Curve C has this equation, a quartic over all real numbers. Let's find dy by dx. Okay, so of course we're using the fact that d by dx of x to the n is n x to the n minus 1. That's our general result for polynomials. So we're going to get 20, we're going to bring the 4 down, 5 times 4, then x to the 3, minus 24 times 3, that's the same as 12 times 6, 72, x squared, plus 84x minus 32. Second derivative, same again. Differentiate this function above. So 60x squared minus 144x plus 84. Verify that C has a stationary point at x equals 1. Okay, we don't want to actually solve this cubic. We just want to substitute in x equals 1. X equals 1 dy by dx equals 20 minus 72 plus 84 minus 32. Add the 20 and the 84, 104. 72 plus 32 is 104, but I'm going to be minusing that. So I get 0. And therefore, it's enough to say C has a stationary point at x equals 1. Part 2, we're asked to show that this stationary point is a point of inflection, giving reasons for our answer. So if you do the second derivative and you get a positive, then you have a minimum. If you get a negative, you have a maximum. If you get 0, then it could be all three. So I'm just going to check it anyway. When x equals 1, d2y by dx squared is going to equal 60 minus 144 plus 84. That is going to equal 0. That actually doesn't tell us it's a point of inflection. It could still be all three of them, because, for example, y equals x to the 4 is a nice example. The second derivative will be 0 at 0, but it's going to give us a minimum. And then minus x to the 4 would give us a maximum, whereas x to the 3 give us a point of inflection. All of these actually have d2y by dx squared equal to 0. So it's not enough. So we need another test. And the one that we typically learn at A-level is to return, forget the second derivative, return to dy by dx. And let's look either side of 1. So when x is equal to 0.9, dy by dx, we'll figure that out in a second. And then we'll also look at x is 1.1. So just to the right and just to the left and just to the right. Now we're going to put that back into this one here. Very important. You don't put it into the second derivative if you're using this approach. Okay, so we get minus 7 over, I just need it to be minus 750 to the left. So what we have at the moment, I'm just going to draw a little diagram, is we have a negative gradient at 0.9, and we have a 0 gradient at 1. So we want to get another negative now when we substitute 1.1 in. And we get minus 1 over 10. So again, it's going to look like that at 1.1. Therefore, it's enough to say there is, so both, and I should probably say both, are negative, or negative either side. Therefore, there is a point of inflection at x equals 1. Note, you can get points of inflection where where it's not a stationary point, okay? But here we're actually classifying a stationary point, so it's enough. Otherwise, you need to show that the second derivative is changing sign, which is a slightly different approach, but this works really well here. So basically, whenever you're classifying a stationary point, try out d2y by dx squared. We kind of knew that it was going to be 0 here, but it's still a good check that we've done it correctly for part A. And then return to the gradient, because it's quite a nice like visual representation of what's going on. We can see the point of inflection just by choosing some points. It's negative, then 0, then negative. Okay, well done. So I'm just going to add a little bit onto the end. So the mark scheme allows other ways to classify the stationary point. Like I did say, a general point of inflection was when the second derivative changes sign. So you could look at the second derivative either side and show that it's greater than 0 to the left. I mean, I went with 0.9, they've gone with 0.8, and less than 0 to the right. That would also prove a point of inflection. There are advantages to this method, to be fair, because then you don't have to like remember this dy by dx one, which sometimes people kind of get mixed up. You can just remember in general a point of inflection is where the second derivative changes sign. And yeah, because you might have to do that elsewhere anyway. Just one other thing, I didn't even know about this one, but you could find the third derivative, and then we've got the second derivative is 0, but the third derivative is not equal to 0, and that apparently implies, again, that there's a point of inflection. I haven't quite got my head around that one, but I think this is a fact as well. Never seen that before, so quite interesting. I wouldn't say necessarily use that one, but maybe if you're interested, read a little bit about it, and then I probably still would stick with the first two that I went through.